At exactly 17:23 on June 5, 2025, an Israeli F-16 pilot received a three-word message that would shatter the evening calm of Etalata. Time to go. Within minutes, four of Israel's most advanced fighter jets would carry out the most brazen escalation yet precision strikes on Beirut's densely populated suburbs on the eve of Islam's holiest celebration. The pilot had been strapped into his cockpit for 12 minutes. The Pratt & Whitney F-100 engine idling as ground crews completed final weapons checks. Beneath each wing hung two Rafael Spice 2000 guided bombs, 4,000 pounds of precision munitions capable of threading through a specific window from 60 kilometers away. But tonight's mission would require something far more dangerous than long-range precision. They would have to get close enough to see their targets burn. The F-16I Safa was the only choice for urban strikes. These single-engine multi-role fighters excel at the precision work Beirut's dense neighborhoods demand. Their superior agility allows rapid target transitions in cluttered airspace. More importantly, the F-16I's fuel efficiency permits extended loiter time, critical when holding for 60 minutes while civilians evacuate. At 17:24, the formation leader advances the throttles. The F-10 PW229 engine responds instantly, generating over 29,000 pounds of thrust. Despite the massive payload, the heavily loaded F-16I accelerates down Ramat David's runway at 165 knots. His wingman follows 10 seconds later, then the second pair at identical intervals. By 17:26, all four jets are airborne, climbing through 10,000 feet in a precisely staggered formation. The mission profile demands surgical timing. 8 targets are spread across Beirut's southern suburbs Hadith, Harat Hrik, and Burj al-Barajna, plus 2 more in South Lebanon. Each aircraft carries enough ordnance for 2 targets, leaving zero margin for error. Miss one release window, abort one run, and the entire strike package unravels. By 17:42, exactly 60 minutes before the first bomb falls, Israeli military spokesman Avichai Adri begins posting on social media. These are not encrypted military channels or diplomatic back channels, but Twitter and Telegram. The warnings include satellite photos with red circles around specific buildings, telling anyone there those buildings will become Beirut's latest parking lots within the next hour. This is not psychological warfare. It is legal compliance with a tactical twist. International law suggests warning civilians when feasible, and Israel documents every warning for potential future tribunals. But those 60 minutes create predictable patterns that military planners exploit. Traffic flows become rivers of intelligence, which buildings empty immediately, which show frantic vehicle loading, which remain suspiciously calm. All of this information is valuable. The pilots remain in a holding pattern at 28,000 feet, monitoring encrypted tactical frequencies as intelligence updates flow from reconnaissance assets. Drone footage shows evacuations in real-time, cars fleeing certain buildings while others remain untouched, inadvertently confirming Israeli targeting intelligence. Now all they have to do is wait 60 minutes before releasing one of Israel's most potent weapons. The Rafael Spice 2000 hanging from each F-16I's wing represents the convergence of 3 technological revolutions in one 2,000-pound package. At $200,000 per unit, these bombs cost about as much as a G-Wagon. But unlike Mercedes-Benz, the military is not paying for a brand name. They are paying for what lies inside. Traditional guided bombs rely on GPS, spoof the coordinates, and that expensive bomb cannot hit the right side of a barn. But the Spice 2000 is not a normal bomb. Its primary navigation uses GPS, but that is only the beginning. Inside the nose section, 2 additional guidance systems operate flawlessly, each backing up the others. The inertial navigation system uses ring laser gyroscopes spinning at 400 Hz, precisely measuring rotation. 3 accelerometers track movement in 3 dimensions, calculating position based on the fundamental laws of physics. No outside signals are needed. Even if every GPS satellite vanished, the INS alone could place the bomb within 30 meters of its target. But the next system is where Israeli engineering becomes even more formidable. Electro-optical scene matching technology turns the bomb into a machine with perfect memory. During mission planning, operators upload high-resolution satellite imagery of the target area, every building, every street corner, every distinctive feature within a square kilometer. As the bomb falls, its nose camera captures 60 frames per second, comparing what it sees to what it remembers. The processing power required is staggering. The Spice's computer runs image recognition algorithms that would have required a supercomputer in the 1990s. Edge detection identifies building outlines. Pattern matching locates specific architectural features. Contrast analysis separates targets from backgrounds, all while falling at 300 meters per second, and unfortunately for these targets, their time is up. At 18 o'clock hours, the holding pattern breaks. 4 F-16 is bank east in perfect synchronicity, descending through 20,000 feet as they accelerate toward the Lebanese coast. Beneath their fuselages, the Rafael Sky Shield electronic warfare pods wake from standby mode. Their threat libraries contain the electronic fingerprints of every radar system from here to Tyre. The Lebanese air defense network, a mix of Soviet-era systems, some French units, and recent Chinese imports, lights up. The aging P-18 spoonrest radar at Tyre emits its distinctive VHF pulses. A more modern Chinese JY-27 south of Sidon joins in. Multiple fire control radars probe the sky, searching for something to lock onto. What they detect seems impossible. The lead F-16I appears at 15,000 feet heading north at 350 knots. At the same time, it appears at 25,000 feet heading east at 550 knots. A third return shows it diving through 5,000 feet. The Sky Shield pod is not just jamming, it is deceiving with mathematical precision. Inside each pod, the digital radio frequency memory system captures incoming radar pulses perfectly frequency. Pulse width, modulation, everything then retransmits multiple altered versions. Delay 1 by 3 microseconds and the radar believes the aircraft is 900 meters farther away. Shift the frequency by 200 Hz and the speed appears incorrect. Combine multiple false returns and the radar display becomes chaos. As this continues, the pilots monitor their radar warning receivers as new threats appear. An SA-6 straight flush radar paints them from the Bekaa Valley, its distinctive high-pitched tone sounding in their headsets. The Sky Shield automatically classifies it as a priority threat and allocates more jamming power to its frequency band. The radar warning symbol changes from solid to dashed, the lock is broken. Coordination between all four aircraft amplifies the effect. The formation leader designates itself as the lighthouse, broadcasting powerful jamming across major threat frequencies. The other three operate in Firefly mode, emitting short bursts of jamming that appear and disappear randomly. To Lebanese radar operators, it appears that an entire squadron or more is present. Ground controllers at Beirut Air Traffic Control watch their screens in confusion. Civilian transponders appear normal. A Middle East Airlines flight climbs on schedule. But military radar returns move in impossible ways. Phantom formations appear, race across the screen at Mach 2, and vanish. Real aircraft hide among false signals. At 8:12, the F-16 has reached the release point. Beirut spreads below them. The formation splits into two elements. The leader and wingmen head toward Hadith and Harit Reek. The second pair angles toward Burj al Barajna. Each pilot runs through the same checklist: master arm on, weapons selected, release mode confirmed. The lightning targeting pods move to their assigned targets, infrared sensors cutting through the evening haze. In their headsets, Lebanese search radars grow more active. Pulse frequencies increase. Scan patterns tighten. Someone below senses something is wrong but cannot identify it. The electronic shield holds, concealing the aircraft as they prepare to strike. At 18:18, the lead pilot releases his first Spice 2000. The bomb release sensor confirms separation. The aircraft rises slightly, suddenly lighter by 2,000 pounds. The pilot does not watch. He turns toward the second target. 2 seconds later, the bomb deploys its wings, transforming from a falling object into a guided weapon. Its GPS receiver locks onto 5 satellites. The initial solution places it 2.3 kilometers from the target with 43 seconds to impact. The computer calculates the trajectory. 5 seconds later, the wingman releases his bomb over Harit Reek, His target is a 5-story commercial building that Israeli intelligence identifies as housing drone assembly workshops in its basement. The bomb's camera activates early, capturing the evacuation in thermal detail. Cars fill the streets, people flee on foot. The building appears warmer than those around it, indicating heat from activity below. By 18 and 15 seconds, the sequence continues. 4 bombs are in flight, each pursuing its assigned target with mechanical precision. The formation leader's second weapon is aimed at a Hezbollah logistics site disguised as an auto parts store. The wingman's second release targets what appears to be a community center but is believed to conceal communications equipment 3 floors underground. As the bomb descends through 10,000 feet, its camera activates. The familiar Beirut skyline comes into view: mosque minarets, apartment buildings, and the Mediterranean coastline. The computer compares these features with its stored imagery, calculating its exact position. At 5,000 feet, GPS signals begin to degrade. Lebanese electronic warfare units, likely using Russian-supplied equipment, transmit false signals to mislead the guidance system. The Spice's computer detects the inconsistency immediately. GPS places it 500 meters east of where the inertial navigation system and camera indicate. Without hesitation, it rejects the GPS data, relying instead on its internal navigation and visual guidance. The final phase begins at 1,000 feet. The camera switches to narrow field of view mode, zooming in on the designated building. The algorithm searches for programmed reference points, the ventilation unit on the northwest corner, the distinctive roofline, and the layout of the adjacent parking area. When confidence reaches 98%, the bomb commits to its final approach. The tail fins adjust up to 20 degrees in any direction, making corrections 50 times per second. Crosswinds are compensated. Thermal updrafts from the city are corrected. The bomb guides itself directly to the target, even maneuvering between buildings if required. Few settings programmed at Ramat David determine the detonation method. Impact fuses are used for surface targets, and delayed fuses are used for penetration. Tonight, all are set to delayed. The bombs are designed to penetrate deeply before detonating. Just before 1819 local time, the first impact occurs. The BLU-109 penetrator warhead strikes the building's roof at 267 meters per second. Its hardened steel casing, designed to pierce reinforced structures, passes through the roof with little resistance. It continues through multiple floors before stopping near the basement level, then it detonates. Inside the confined space, the blast pressure cannot disperse normally. It reflects off the concrete walls, increasing in intensity. The floors above lift under the force. Seconds later, the second bomb strikes, followed by the third and fourth. Shockwaves from the explosions interact, amplifying damage in some areas and reducing it in others. By 1820, southern Beirut is filled with rising smoke. Large plumes climb into the evening sky, fed by secondary explosions. The pilots do not remain. They are already departing at low altitude. Lebanese air defense systems activate, but the jamming pods continue to create false targets as the aircraft head toward the Mediterranean. At 1842, as smoke still rises from the southern suburbs, 2 F-15 ROM fighters approach at 30,000 feet. These aircraft form the second wave, carrying heavier weapons. The choice of the F-15 is based on physics. Delivering 5,000-pound penetrator bombs from high altitude requires greater lifting and thrust capability. The F-15's twin F-100PW229 engines produce 58,000 pounds of combined thrust, necessary for maintaining performance under such heavy loads. Maintaining altitude and speed while carrying 10,000 pounds of ordnance per aircraft is demanding. The two-seat configuration proves essential. While the pilot manages the flight profile, the weapons systems officer operates the APG-70 radar and the Lantern targeting pod, ensuring precise delivery. These are not the agile F-15s used earlier over the capital. The F-15 is built for deep strike missions with a 1,600 kilometers combat radius, conformal fuel tanks that minimize drag, and reinforced hardpoints rated for the heaviest weapons in Israel's arsenal. Tonight, that weapon is the GBU-28. Each aircraft carries 2 GBU-28 bombs. At 5,000 pounds each, they are massive penetrators filled with explosives. The warhead casing is machined from hardened steel alloy, designed to remain intact while penetrating up to 6 meters of reinforced concrete or 30 meters of earth. Only the F-15 has the payload capacity and high-altitude performance to deliver them effectively. Their target tonight is buried deep beneath a hillside near Al-Qa. Satellite imagery over the past 6 months has shown unusual construction activity, dump trucks arriving loaded and leaving empty, ventilation shafts appearing in remote areas, and power lines running to seemingly vacant terrain. Israeli intelligence assesses the site as a probable command bunker, possibly a manufacturing facility. The F-15 PG-70 radar scans the area in synthetic aperture mode, creating a detailed ground map despite the darkness. The weapon systems. Officer coordinates with the second aircraft to ensure their bombs will strike different sections of the underground structure. At 1844, the lead F-15 begins its attack run. Unlike the F-16 strikes, the GBU-28 requires high altitude to achieve maximum penetration speed. Released from 35,000 feet, it accelerates toward the ground, converting altitude into destructive kinetic energy. The pilot releases both bombs in quick succession. 10,000 pounds of ordnance separate from the aircraft and begin falling toward the hillside. Initially, GPS and inertial navigation guide the bombs, adjusting their path through small fin movements. At 2,000 feet, laser guidance activates. The targeting pod illuminates the impact point with coded laser energy. The bomb detects the reflected signal and makes final corrections. Moments later, the first GBU-28 strikes the hillside at 312 meters per second. Soil and rock offer little resistance. The penetrator drives deeper 15 meters, 20 meters, 25 meters until it reaches the bunker ceiling, protected by reinforced concrete. The penetrator breaks through. The delay fuse allows the bomb to travel deeper before detonation. Half a second later, 630 kilograms of explosive detonate inside. 2 seconds later, the second GBU-28 strikes 40 meters away, penetrating another section of the underground complex. Its explosion combines with the first, increasing the destructive effect underground. Secondary explosions follow as stored materials ignite. At 1845, the hillside erupts. The ground lifts and collapses, leaving a crater 60 meters wide. What had been hidden underground is destroyed.